So we've already been introduced to the MVT for integrals. We know it has something to do with the average value of a function. Oops, get rid of that. Okay, but I want to talk a little bit more in depth about that and where that formula comes from. And to do that, we're going to start by thinking about a trapezoid. We know that a trapezoid has an area formula that is the average of the bases, so b1 plus b2 over over 2, and then times the height, okay? And so this is our base 1, this is base 2, and then height is the distance between those two bases. And finding the average of the bases gives us the mid-segment, the length of the mid-segment, okay? If you remember from geometry, mid-segment is formed by averaging your bases, okay? So that's exactly what this length is. And the idea for developing the formula for the area of a trapezoid comes from comparing it to a rectangle that has the same area. So because of, you know, some geometry things that we can do, like the additive properties with area and stuff, we could cut off these little triangles right here, and we could kind of swing them around and fill them in up here, and we would end up with one rectangle whose height is the exact same as the trapezoid's height, and whose base, this length right here, is the length of the mid-segment, or the average of the bases. So this right here is the mid-segment, okay? So in other words, we are getting our formula for the area of a trapezoid by asking ourselves, what are the dimensions of a rectangle that has the same area? Okay, because we know the area of a rectangle, and area for everything is based on rectangles in geometry, okay? And so we can expand that a little bit more to talk about the area of this region. So this is not exactly a trapezoid, but if you turn your head sideways, it looks a little bit like a trapezoid, and you can imagine that we have like a, you know, kind of a straight segment here. Now one side is going to be curved, and that's okay, but it's still, we can see how it's kind of similar to a trapezoid. The height on any trapezoid is the distance between the two bases, and the two bases are the parallel pieces. So this right here would represent the height of the trapezoid. Okay, height does not always mean up and down. It means distance between the bases when we're in geometry. Okay, and then the length of these two would be our B1 and B2. Now, because this is not linear, we don't have a height. We can't just say, well, the average of this height and this height is the average height of the entire thing. So that's where this average value piece comes in. That's what we're looking for, okay? In other words, if we were to be able to average the infinite number of heights of the function along the curve f of x from a to b, if we could average out all of those heights, so take this height plus the next one plus the next one, add all of those and divide by however many we have, okay, we would get the average height of the function, okay? In other words, the average value of the function, all right? And I don't know where that's going to fall. Let's just say it's somewhere right around here. I'm just guessing, okay? And I'm labeling that with F and then subscript AVG for average, okay? So it looks like this right here, all right? So whatever this height is, okay, there has to be, not totally drawn to scale, but that's okay. There has to be a rectangle that has the same area as the area under that curve, okay? And then the dimensions of that rectangle, well, this distance is the same, okay? And then this distance right here is whatever the height of that, of the average value is, okay? All right, so area of a rectangle with a height of whatever the average value is, well, area of a rectangle is just length times width, so we can say that's going to be equal to the average value times, and then this distance right here we're not going to call h because we need that in the context of the graph, and so this distance right here is the distance from a to b, so we're going to write that as b minus a. Okay, and we also know that this rectangle has the same area as this region under the curve. Now I am saying area because this is a positive function over the interval from a to b. If any of that graph would drop below the x-axis on this interval, all of this is still true, except we would describe it and specifically say net area, okay? So it is okay to go ahead and say area, even though part of that function might be below the axis. All right, and what we know is that this is going to, the area of this rectangle is equal to the area under that curve, which because of our definition of the definite integral coming from the infinite Riemann sum, we know to be the integral from a to b of f of x dx. Okay, so this right here is like my length times width, and I know that's equal of the rectangle, and I know that that's equal to the area under the curve. So in other words, that's equal to all of this. Okay? Let me get rid of that though. Okay, so taking this equation, if I want to solve for the average value of the function, then what I'm trying to do is I'm trying to isolate this piece right here, meaning I need to divide both sides of the equation by b minus a. Okay, so that tells me that the average value is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, now you could put the integral and then put a giant fraction bar and put b minus a under there. It doesn't really matter. We usually write it out in front though, because integrals inside fractions get a little complicated looking, okay, but it's the same thing, all right? So this tells us that if we want to find the average value of any function over an interval, we can find the definite integral over that interval and then divide by the distance between the two ends of the interval. Okay, so make sure you learn this formula, and let's go ahead and do a couple examples. So for the first one, it says find the average value of the function f of x equals 5x squared on the interval from a to 4. So this is our a to b, this is our f of x. So plugging straight into this formula, we get that the average value is equal to 1 over 4 minus 1 times the integral from 1 to 4 of 5x squared dx. Okay, so that's 1/3 times, and then I'm using the power rule here. Antiderivative here is going to be 5/3 x cubed. Remember, add 1 to the exponent, then divide by the new exponent. 5 is still just a coefficient there, and we are evaluating over the interval from 1 to 4. So we end up with 5 over 9 times 4 cubed, which is 64, minus 1 cubed, which is 1, so that's 63, and 9 reduces to 7, so 35 is the average value of that function. So that's just a straightforward application of finding the average value of the function using this formula. What we want to do next is we want to look at MVT, okay? Now, there's actually two parts to the MVT. We have seen one of them extensively back in Unit 3, and then we also saw the introduction to the MVT using integrals when we did the 4.3 proof of the fundamental theorem, okay? But I'm going to refresh on both of those. So MVT for derivative says if f is continuous on the closed interval and differentiable on the open interval, then there exists a c in the interval, in the open interval from a to b, such that f prime of, I'll come over here, the f prime of c is equal to f of b minus f of a over b minus a, okay? In other words, we could say, in English, we could say the instantaneous, oops, that's not how you spell instantaneous, instantaneous rate of change is equal to the average rate of change. Okay, there has to be a point where the instantaneous rate of change is equal to the average rate of change. Now, if we extend that to integrals, okay, and instead of a rate of change, we're now talking about the value of a function. So here we are saying, let's add this, MVT specifically for integrals. Now, by the way, a problem may, even if it says to use the MVT, may not clarify whether you are looking at derivatives or integrals. So you just need to pay attention to whether you're talking about rates of change or values of a function, okay? So for integrals, we would say if f is continuous, and by the way, we do not care if it's differentiable or not, it just has to be continuous, okay, on the closed interval, then there exists a c in the open interval from a to b, oops, such that f of c is equal to the average value, which is 1 over b minus a times the integral from a to b of f of x dx. Okay? Or in English, we could say there's a c where the instantaneous value is equal to the average value. Okay? Let's scroll back to the picture and look at this and see what it means for this problem. So what this means is it just guarantees the existence of this point. Okay, so we'll call C that value right there. It guarantees the existence of this point where the height at this point, so f of C, is equal to the average value of the function. Okay, this is only true if a function is continuous. Okay, a real quick example of a discontinuous function and how it would not apply would be if you think about a step function. Okay, from 0 to 1, from 0 to 2, the average value of this function is going to be 1/2, but there is no point where the output of the greatest integer function is 1/2. Okay, so the MVT would not apply there. All right, but if the function is continuous, there has to be an x-coordinate, there has to be an input where the output is equal to the average value of the function. Okay? All right, so not only can we determine if the MVT applies by checking to see if there's a point, checking to see if the function is continuous on the closed interval, but we can also find the values that would satisfy the MVT. Okay, so here let's double check, does MVT apply? Yes, it does, because that's a continuous function on this interval, in fact everywhere. So then what we want to do is we want to find the average value, set that equal to f of c, and solve for any possible c. Now c does need to be in the open interval. All right, so the average value is the integral from, in this case, -1 to 1 of x squared dx. So using the second fundamental theorem to evaluate, we've got 1/3 x cubed evaluated from -1 to +1. So 1/3 times 1 minus -1, which is 2, so 2/3. Okay, so the average value of the function is 2/3. Then we take that and we set that equal to f of c, which is c squared. So then c is equal to plus or minus root 2/3. Now let's double check. Are both of these numbers positive root 2/3 and negative root 2/3 in the interval from -1 to +1? Yes, they are. So there are actually two values that satisfy the MVT for that integral.